Hey guys, your boy Chilla here. Welcome back. Well, not really back. I guess this isn't part of any particular series. It's its own kind of thing. But if you've been following the channel in the past few weeks, you've noticed I've been putting out videos on ACO. And in the most recent one, as of recording this video, I was doing coroutines with ACO. And that's probably like the most fundamental use case of coroutines. When you want to demonstrate what's a coroutine, why would you want to use it? You demonstrate it with asynchronous, particularly with networking. But that's not the only thing you can use coroutines for, and that's what I wanted to show in this video. So we're going to use coroutines for something else. We're going to use them to script the movement to basically animate a sprite on the screen, move it around in a certain pattern, in a certain fixed sequence. Now, you know me, I don't just demonstrate a thing, I also want to do a little setup. So I want to show you what's the alternative, what's the prior art, the thing that we are improving on with coroutines. Why would we use coroutines? What were we using before we had coroutines? And the thing we were using is a state machine usually. To do animation like this, you create like a state machine. So let's start by animating a sprite with a state machine. Let me just give you a quick tour of what we're starting with here. It's the Chill framework. This is kind of like an experimental branch where I'm doing a little prototype of my simple layer. So very simple interface into graphics and windows and stuff like that. But here is the basic entry point of our program. We initialize the window and all the graphic stuff. We load a sprite from a PNG and we create a sprite frame of that, and then we can draw that frame to the screen, to a sprite batch. So we call begin frame, and then we draw a bunch of this, and then we call end. And we do that in a loop until we detect that the window is closing, and then we exit. And if you run that, it looks like this. Very simple. That's our starting point. Now, there's one more thing that I have added, and that is this Sprite class. And it's just a wrapper around the sprite frame that you saw in that previous example, but it also adds position, direction, speed information. So it has an update function where you can update the sprite every frame, and it moves around depending on what direction it was set in. And it encapsulates the draw function. So this is what we're going to be using. So let's put that in here. That will be our starting point. We include sprite. We've already been doing that. So now instead of creating the sprite frame, we're just going to create our sprite. And then in our loop here, we can do s.draw. And we should get a sprite in the middle of the screen. There we go. One sprite in the middle of the screen, just as ordered. And if we wanted to move that bad boy, we could say, okay, we're going to set its direction. So set dir. And we'll just make it move to the right. And if we want to do that, then we should update it every frame. So we can call update. This is not taking into account any time step or anything. It's very simple. So now we got a sprite that's sliding all the way over to the right of the screen. All right. So now what we want to do is we want to, instead of doing that sliding, we want to make it move in a particular pattern. And the pattern that I want to do is a triangle. So just move in a triangle. So first things first, in sprite.h, let's add just a little helper function. It's going to make our life easier. We're going to call this one send sprite to. And when you call this on a sprite, every frame, it's going to set the direction that sprite is moving in so that it goes to the place where we want it to go to. So now here in my logic loop, if I go send sprite to, and I'll send my sprite to, I don't know, like 100, 100. It should move there, but then when it gets there, it should stop. Okay, we're going to try 200, 200 here. It just kind of goes there, right? So something's screwed up. All right, fair enough. It's already gone off the rails here. Let's see. Sprite. Basically, the idea is when you update it, you take the direction, but you want to clamp it so that if it's greater than 1, you only use the vector of length 1. And the reason you do that is so that if I just do like a displacement vector that's really long, it's not going to multiply that by the speed and you're not going to just jump there. But we're just jumping there. So obviously this get clamped is kind of messed up. So let's see in here. So we're doing a maximum magnitude here. If the length, which is mag, is greater than the maximum, then we want to divide by the maximum, which is 1. That doesn't make any sense. We want to divide by the magnitude. I think we want to divide by the magnitude divided by the maximum magnitude. That makes more sense. Okay, let's run this. There we go. And he's going to move and then he's going to stop. There we go. Perfect. So that is one of our basic building blocks. So basically we want to script a sequence of these send sprite twos to different locations, but they have to be spaced out over many frames. So essentially what I want him to do is I want him to trace out a triangle on the screen about some center point. So he wants to start here at the top and then go right, left, go back to the top. But if he's somewhere else, he has to actually travel to the start point first. So travel to the top, then go right, left, and then go back to the top. So that's why we've got 4 states in here. Constructor takes the center of the triangle that we want to trace out and the size of it, how big it's going to be. And we calculate our 3 waypoints. And then in our state machine, all we're doing is we're checking, are we at our destination? If so, we're going to go to the next state. If not, we're just going to call send sprite to whatever the destination is, the waypoint. Actually, I think we need another going top end. And let's add another state, done. So going top start feeds into going right feeds into going left. This, I just copy and pasted this from a little test that I did, but this was doing it in an infinite loop, but we don't want to do that. We want this state machine to run once and then end. So we need to add another state. So going left should then trigger into going top end. And case done should just break and not do anything. Well, I mean, we could just do sprite dot set direction 0, 0. So if you do happen to call update on a sprite that is done, it should just stay at its final position. It shouldn't keep moving with the previous direction that was set on it. All right, so that's good. So the final one should be done. Here we go. So here's our state machine. It's a very simple, linear sequence. There's no loops in it. There's no branches in the state diagram. The initial state should be going top start. We want to add one more function in here, which is to check to see if it's done. We do bool is done const return state is equal to state done. There we go. Okay, so here's our state machine. This is the simplest state machine you're going to see. Very easy. Now we just create it. So we create our sprite. Let's create our triangle machine. What's the destination? So we'll put it at 200, 200, somewhere in the top right quadrant, and we'll make the size 100. That seems fine. And now all we do is for our sprite, we go tm step, give it the sprite. And then the state machine will calculate what motion we should set on the sprite, and then we update the sprite's position, and then we draw, and everything is good. So we run this, at least it compiled. Let's go. So we go there, hit our start point, we trace out our triangle, and we're done. We stop here. If we wanted to be fancy with it, we could even tell it to exit the program, exit the loop when it's done. So while not is closing and not tm.is done. There he goes, making his triangle. He's at his home, and we close the program. Very simple. So there you go. There's your state machine to do a very simple motion. Now, here's the thing. I don't just want to do triangles. Let's say I want to do like a serpentine motion like this. What do I have to do? Well, trying to put it into the triangle machine seems like a dumb idea. So now I got to create another state machine, a serpentine machine. And I probably want the ability to like repeat the triangle motion, like do it n times or do it just forever. And I mean, there's a couple of ways you could do that. You could put a repetitions in here, like int n, and then in the state machine, you could basically check when you reach this one, check if you're going to be done or if you're going to loop back up here, increment the count and then loop back up here. So now you've got 2 state variables. You're multiplying state by state, which makes the state machine more complicated. But it's a fairly simple option. Another option that's not as simple is to say, okay, well, this state machine only does 1 iteration and then it's done. But we now have a second layer. We have another state machine that runs this state machine, this substate. So triangle machine becomes a substate of the overall behavior script state machine, which will run the triangle machine n times. Now that's more complicated than, putting the count in here, but it's actually more useful because what if we wanted a composite sequence of motions? Like let's say I want to do a triangle here, then I want to do a triangle down here, then I want to do a serpentine over here, and I want to loop this triangle 4 times, this one twice, and just do my serpentine. So in that case, you really do want nested state. You want an overall state machine that, orchestrates, okay, we're going to do a triangle here, n times, then a serpentine, and then you have internal nested state machines that do the individual actions, like do a triangle path, do a serpentine path. So now we're getting into nested state machines. Now, if we want to do that, the external state machine is going to have to hold what is the current active nested one. And they are going to be different types. So you're going to need polymorphism. You're going to need to virtualize your step function and your is done. Or you're going to have to use like something like a variant. So things are very quickly getting complicated. What if we want to script, like multiple entities individually, each with their own state sequence, or coordinate them? This is becoming very complicated. And the thing is about these state machines is, it's not that complicated, but it's difficult to read and to edit going through. Like, this is essentially just a very simple sequence of 4 actions. But look at how much code it takes when you want to script it as a state machine. It's a lot more complicated. And I think you know where I'm going with this, right? Because if you've looked at my ACO, you saw that the callback system became a lot simpler and it just became a very simple sequence of statements when we rewrote it as a coroutine. And you also heard in that video that you can transform state machines into coroutines. They are basically equivalent. So can we transform this state machine into a coroutine? And obviously the answer is yes, because you looked at the title of the video. So let's do that. All right, here's our starting point for coroutines. I added this header source pair here, copy and pasted from state machine mode, removed all the state machine specific stuff. So now if we run the thing in state machine mode, it runs as you would expect, makes a triangle and closes. But if we run it in generator coro mode, it's going to run the other routine, which currently isn't doing jack shit. So how do we get our coroutines? Like I said before, the support that's directly in the language is incredibly low level and is obtuse to use. So you generally want to use it with a library, either with a standard library, which doesn't really have much stuff in it yet, or a third-party library. And the third-party library that we're going to look at today is cppcoro. It's kind of out of date, so I wouldn't actually use it for anything real, but it's going to be very good for demonstrating just what I want to show in this video. So the way they implemented coroutine in C++ is they gave you a lot of options to customize the behavior of a coroutine. You can build coroutine types that behave in very different ways. And so no 2 coroutine types you can't expect them to really work the same way. They all have their own way of working that is, very well suited to the problem they're trying to solve. And the one that we're going to look at today is a generator type. So a generator, typically you access it like a sequence, like a range. So you can just loop over it. And the most basic demonstration is usually it just generates you a sequence of values. So here we have a Fibonacci generator. And the thing about the Fibonacci sequence is it's unending. So if you were to try to create that sequence as a vector and then allow someone to loop over it, you can't do that because you don't know how many they actually need. They would have to specify first how many they're going to loop over, and then they would start looping after you generated the whole thing. Whereas with a generator, it just creates each element lazily as it is requested. So if we look at this generator here, it's got an infinite loop and it's got this co-yield. So what this does is every time you dereference the iterator, it is going to run your generator until it hits yield, and then it's going to return that value. So for every iteration of this range-based for loop, it is running through this loop once and then pausing the coroutine, yielding you back the value. So we're going to use this for our frame. We're going to get it to yield once every frame. Every frame, we are going to basically dereference the iterator on this generator, get it to run. It's going to yield once. Now, we don't actually need a value because all the generator is going to be doing is it's going to be working directly on the sprite. So it's going to return a dummy value. The important part is that it is going to co-yield so that it can pause its sequence. Now, the other important thing is that we want to build our sequences with subsequences. Like if we want to script, like if we want to choreograph, do a triangle here, then move down here, do a triangle, then do a serpentine. Want to choreograph multiple things, we're going to have a generator that is going to call sub-generators. So this generator doesn't allow you to do that. It doesn't allow you, basically what you want to be able to do is to yield the result of a different generator. So you can do that with a recursive generator. Generator is actually in C++ as of C++ 23, in experimental on MSVC, but I don't think it allows you to do recursive, so we can't use that one. That's why I'm pulling in cppcoro. So enough John, let's just do the code. So we're going to pull in cppcoro from VC package, and that should build. Once it's built, we can get access to those headers. Okay, that ran without issue. So now I should be able to include in here, do it like this, cppcoro. There it is. And let me see, what do I need? I need recursive generator. So that's in there. Create a little namespace alias there for me. So let's build a few like just fundamental types. So whenever we want to wait until the next frame, we should just yield our coroutine. We just got to yield a dummy value. So let's do recursive generator, and we'll just do int for the dummy value. We're going to make a coroutine wait next frame. And it's just going to co-yield 0. So there we go. That's what we do. We yield this when we want to just finish and wait for the next frame in our sequence. Now let's create a coroutine that is a sequence that just moves a sprite from wherever it is to another point. So it's called move sprite to. It takes in the sprite and it takes in the target point that we want to move it to. Now we're going to do a loop. Let's do a while true loop here. So we subtract from the target the current position of sprite. We get an offset vector. And we're going to check to make sure that offset vector's length is greater than 1, meaning we're not at that point yet. If it's less than 1, we consider ourselves at that point. So if it's greater than or equal to 1, we got to send the sprite to that point. So we call send sprite to give the sprite instructions to move towards that point. And then we call co-yield wait next frame. So if we're not there, we instruct the sprite to move towards that point and we wait till the next frame. We're going to check again. Now if we are there, then we got to exit out of this coroutine because we're done. We got to do the next thing. We've moved there, so we're finished this operation. Now let's create our actual triangulate coroutine. So this is going to tell the thing to move in a triangle shape. So we'll give it the same interface that we had for the state machine one. So it takes in the center, it takes in a scale, and it's going to move to the top of that triangle centered there, and then trace out a triangle. So let's start off by calculating our waypoints up front, and then it couldn't be easier. So first we're going to move the sprite to the top. That's our starting point. Then we're going to go right, left, top. So do right, left, top. And that's it. There it is. There's the triangulate. This is equivalent to this coroutine here with a definition of an enumeration, constructor, step function, is done function. All that just becomes this. Well, what do you think? I think it's pretty good, right? Now, here's the trick. So, in order to run this thing, generator runs on iterators. So we need to iterate over it. We don't care about the value because obviously the value yielded is always just a dummy 0. But we do have to iterate over it. So we can iterate over it using a while loop. We could use a for each loop, right? A range-based for loop. So for auto, D for dummy, in triangulate, S, center point at, size is 100. So we triangulate in this loop, call update, and there you go. This should do more or less the same thing we were doing before. Well, it would if it didn't build. Okay, yeah. So one of the reasons why I said that I don't recommend using cppcoro in a real project is because it is really out of date. So for example, it actually uses the experimental headers for coroutine. So by default, it's not going to work with a modern compiler. But what we could do is we could go into this source file here, special for you, and we could say, okay, C++, what's the command line? If we put this switch here, we put await in there. That will enable the experimental ones that have, they've been deprecated. There you go. So that builds So if we are running in generator coro mode, we should see similar behavior. We move to the top of our triangle, we trace out our triangle, and we're done. And then it exits because the coroutine has finished. There's no more values. It returns the end iterator, and this exits. Exactly the same, but a lot cleaner. This is a lot nicer. And you don't have to put it in here. You could get the iterator out and iterate over it, so you could do multiple ones or whatever. But this is the cleanest way I could show it. But wait, we're just getting started, because remember all that stuff I said, how difficult it would be to, implement multiple different patterns and then to choreograph sequences of different patterns together? Well, we're going to do that right now, and you're going to see how easy it is. So here's the coroutine for a serpentine pattern. It's one iteration of serpentine, which means you start here at the top left, you go right, you go down, you go left, you go down, and then you can chain these together. Now this one works a little different than triangulate in that it works on your current position. So you don't tell it a start position. Wherever you are, it will consider that the start, and then it's going to go right by width, down by height, left by width, down by height. And you could repeat that pattern n times to do an n serpentine if you wanted. And now let's create a coroutine that calls these two coroutines to choreograph a sequence. So here it's called behavior, and you can repeat n times before it finishes, and it is going to do a triangle. In one spot, it's going to do a triangle, triangle, then it's going to move to a different spot, and then it's going to do 3 iterations of the serpentine, and it's going to go back and do it all again. Now this is going to take a while, so I'm going to go into Sprite here, and I am going to edit its speed to be 2, just so that we're not here forever. And let's see here. Now we change this from triangulate, we just change it to behavior. We're going to put the number of reps at 3, so it'll run it 3 times, and then it should exit. And let's build. All right, here we go. Here's our complex sequence. There's one triangle. We go to the second triangle. We go to the third triangle. Now we do our serpentine. There, we're doing our serpentine. There's 3 iterations of serpentine. Go back, do the first triangle again. Okay, here we are in our third iteration, second triangle, third triangle, and the serpentine. And it should close after it finishes this one. There you go. So I think that's pretty much what I wanted to show you here. I'm not just recording something in post here. I missed a little thing. Let me show you something. I changed the sequence a little bit, so I made one of the triangulates loop 4 times, and it looks cool. But anyways, let's see. So we do our first triangulate here, yeah, and then we're gonna go to the second one, yeah. Now we're going to go to the third one. We're going to do it 4 times. Zoom, 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 zoom. Isn't that cool? Okay, so now I'm done. I want to leave. I don't want to see it because it's going to loop. This whole sequence is going to loop 3 times again. Oh no, I'm stuck here forever. Yeah, so because we made our loop run the generator, now, yeah, we have a little bit of a problem here. And there's a couple ways you could solve it. Probably the best way is just to the loop on the window condition, run the generator using the iterator directly. But I'm lazy, so what I'm going to do instead is if window is closing, break. So that's the other way you can handle that. So we're going to watch this. I'm going to make you watch it again because I find the little loop on the triangle there so satisfying. Look at him go. Zoom, zoom, zoom. Okay, we're done. Now we want to close it, and all is good. There you go. I just wanted to show you that. So scripting an animation sequence, across many frames with different state transitions, it becomes a lot simpler when you can write it as coroutines. It's a lot less code to write. Imagine what this would look like if I did it all with state machines. But also, when you come back to this code later on, or someone has to edit your code, it's a lot easier to follow this than it is to follow a goddamn state machine. But yeah, that's about it for this video. Let me know what you think. If you're liking this coroutine stuff, you want to see more, or you're like, I'm not really feeling the coroutines, Chili. Because if there's a lot of demand for it, I might look into, okay, well, how do you implement the coroutines now at the compiler support level? Because that's a different ballpark. It's much more difficult. There's a lot of ways you can screw yourself over, but it's also very interesting. It's a fun toy to tinker with, I think. Anyway, until then, thanks for watching. Hope you enjoyed this video. If you did, please click the like button. It helps a lot. And I will see you again with some more C++, maybe coroutines.